These are my solutions for the problems in Matlab Simulation Session 1. In the problem sheet, we are given the Suave modification of the Redlich-Kwong equation of state, or RKS. We can rearrange this so that the right-hand side is equal to 0. For a given temperature and pressure, we can solve for the molar volume V, which are the roots of this equation. So here you can see that this equation is cubic with respect to V. That's why, if you remember, RKS is one of the several cubic equations of state. In Matlab, we need to implement this as a function that returns y equal to pv cubed minus rtv squared, and so on. And then pass this function to f0 in Matlab to get the roots. So this is the function that do that. It takes the molar volume V as an input argument and returns y, which is our rearranged RKS equation. We need to provide the values of the parameters in the equation before y is evaluated. So here are the given pressure and temperature, the critical pressure and the critical temperature, from which we can calculate the constants A and B in the RKS equation. The temperature and eccentric factor omega are used to calculate alpha, which introduces the temperature dependence into the term that accounts for interactions between the molecules. We define all of these parameters inside the function because the function does not have access to any parameters outside this function. It can only see V, which is the input we provided. Also, all variables and parameters that you declare or define inside this function, apart from y, which is what the function returns, are local to this function. So you cannot use them outside this function. For example, in your Matlab workspace or script files. You should know this from your Matlab basics, so please make sure you still know how to write script files and function files in Matlab. Once you define this in Matlab as a function, you need to save it and follow the procedure on the next slide. So if you save the function as molar underscore volume.m, then you just need to type the line here into the Matlab command prompt. F0 finds the roots of the given function. We pass in our function molar underscore volume, and the 0 tells F0 to use an initial guess of V equal to 0. If you try various initial guesses between 0 and 1, you will find 3 roots. The smallest root is the liquid molar volume at 0.1869 liters per mole. An intermediate solution is 0.2515, and the vapor molar volume is 1.3851 liters per mole. There are 3 roots because it is a cubic equation, and we are below the critical temperature. So remember that the given temperature is 400 Kelvin compared to the critical temperature of 425 Kelvin. There are always 3 roots below the critical point giving the liquid and vapor volumes. The root in the middle is unstable, so we never see this state. When above the critical temperature, there is only one root, as the isotherms on the PV chart have no turning points. The solution when the temperature is 450 Kelvin is 1.7480 liters per mole, which you always get no matter what the initial guess is. The second problem asks you to solve a batch reaction problem with a rate given by negative RA, so the rate of consumption of reactant A. This is equal to K, the rate constant times the concentration of A. And the units are mole per m cube per second. Okay, and then we need to write our material balance. So the general material balance is, okay, so accumulation term, this is equal to in minus out plus the generation term. Okay, so in this problem, we don't have any ingoing or incoming or outgoing streams. So we can drop these terms out. Okay, and then we just need to write out the expressions for the accumulation and generation terms. So accumulation term, so that is the change in the concentration of A with time. Okay, but I would like the unit of this to be mole per second. So I need to multiply this by the volume. Okay, so this is equal to the generation term. So the generation term is the rate of consumption of RA. So the units of this are mole per cubic meter per second. So again, I need to multiply this by the volume so that the units of each term are mole per second. Okay, and then RA is given by this. So I can write this as negative V K CA. Okay, so we can cancel the V's. And our model will become dCA dt equal to negative K CA. So now we need to solve our simple model in Matlab. To solve it using an ODE solver in Matlab, we need to define a function that returns the right-hand side of the equation, the rate of change of the dependent variable. This function is shown here. You have to make it a function of t and the dependent variable, which I called just c in this case. So the function defines the rate constant k and then returns negative k times c. So next, you have to solve it using an ODE solver. And for this, you need to set up a few things. First are the starting and end times for the integration. So these are T0 equal to 0 and TF, the final time, equal to 200 seconds. The other thing you need to solve the ODE is an initial condition. This is given as 70 mole per cubic meter in the problem and is defined here as C0. The line in the middle calls one of the Matlab ODE solvers. So in this case, ODE 45. ODE 45 is based on the Rangakuta method, which Dr. Pranav Singh will teach you in your numerical methods. You should also remember this function from your previous modules where you used Matlab. So you passed it the name of the function, the one defined on the last slide. The time interval is the next argument. And finally, the initial condition is the last argument. The last four lines just plot the results. You can save the script on the previous slide and run it to get the results shown here. As I said, ODE 45 solves a system of equations of the form y dot, which is dy over dt equal to f, so function of t, your independent variable, and your dependent variable y. So we need to define the function f and pass it to ODE 45 to solve. Our function was called batch underscore func1 and returned f as the variable c dot. So since we defined f t, so our dependent variable is c, this is equal to c dot equal to negative kc. The equation the ODE 45 solved was y dot is equal to negative ky, or, okay, so using our dependent variable dc over dt equal to negative kc, which is the equation we needed to solve for this problem.